from the University. Oh, wait. Yes. Okay. So we're from the University of Washington in Seattle, and our club is called Society for Advanced Rocket Propulsion.
Okay.
Yes.
Okay, perfect.
So, yes. So I'm Bianca. I'm the program manager.
I'm Marco. I'm the chief engineer.
I'm Jonathan. I am the Nosecone project lead.
I'm Beckett. I'm Finn's lead.
I'm Jonah. I'm Airframe's lead. I'm Anthony. I'm one of the integration leads.
My name is Matthew. I'm the Nosecone coupler lead.
I'm Ashlyn, and I'm the propulsion lead.
I'm Alex, and I'm the recovery lead.
Perfect. Nice to meet you guys.
And then, yes, nice to meet you too. And then our payload lead, Gavin, he's not here right now, but his part will be presented by Ashlyn.
Okay, perfect. Well, my name is Walter Arens. I'm from Mexico. I perfect of Tripoli, Mexico. I am part of ERA. And everything do you need, just tell me about the review. And when are you ready, you can start.
Awesome. Thank you.
All right. So just a general overview of our status. So we are competing in the 10K COTS category. All of our progress reports and fees have been submitted on time. We actually completed a test launch on the 28th of April, and we have completed our final design with our test flight revisions. Currently, right now, we have our parts here to show you. We're at 65% progress on manufacturing our competition rocket. And in terms of logistics for Spaceport, all of our travel and lodging has been sorted, and we have a day-to-day itinerary that goes over time, safety, and proper clothing.
Okay. Perfect.
Here's our general rocket overview. Over here, you can see the dimensions, and on the bottom, you will see a whole holistic view of our rocket. On the left side, you'll see our pi-bonded fins. We have 3 carbon fiber airframes. And on the right, you'll see an aluminum nose cone coupler, which houses our payload and our recovery electronics. And then on the far right, you'll see our 3D printed polycarbonate nose cone, which houses our chutes.
Okay.
Here is our simulated performance. We're running a M2500 motor. We have a projected apogee of 11,000 feet, and our competition configuration of our rocket is kept nearly identical in weight to our test launch, which was also projecting to be around 11,000 feet from our simulations, and in actuality was closer to 10,100 feet. So as a result, our rocket is expected to remain within 200 feet of the 10K target because of the similar flight conditions in New Mexico and Brothers, Oregon, which is where we launched from. And right below, you'll see some of our launch parameters. For example, 109 feet per second off the launch rail, 3.57 max stability, and I'll continue. So when we look at our differences between our test flight design and our competition design, when you look over the left, that is what we flew for our test flight. This test flight featured an aluminum thrust plate that joined the upper fin can and the upper body tube, as well as a composite coupler that joined the lower fin can and upper fin can. The nose cone coupler featured tubes that only extended 5 inches into the upper body tube and nose cone. So with the competition design, the nose cone coupler is in total compliance with longer tubes, so it's all good there. And the bigger difference is that we have another composite coupler that joins the upper fin can and upper body tube, as well as another composite coupler that joins the lower fin can and upper fin can. And you'll see there that the thrust plate is scrapped and the motor is held by the aft ring enclosure. Okay, it's still, but the motor is held by the aft ring enclosure. The centering ring is aluminum to account for weight, for the weight loss, and the new parachutes are from a supplier.
Ask if you can still hear you.
Can you still hear us? Okay.
Okay.
We just have some background noise. Just want to make sure you can hear.
Okay, no problem. You can continue.
Okay. And then, so here were our test flight results. As I was saying before, our test configuration reached an apogee of 10,100 feet compared to a simulated apogee of 11,076 feet. So that's within 1% of target apogee. Our payload survived impact with the ground, and our drogue chute deployed nominally, and our recovery avionics and mechanisms operated nominally. So some things that we can improve on are one, the main chute rigging. The parachute failed to deploy due to shroud line fouling. Our payload camera live stream connection was lost after launch. The integration design was fairly untested. And our fin bonding, you can see on the top right picture that the post-flight damages shows a weak bond between the fins and airframe. You can see a very cleaned separation there. So we'll talk about our improvements for that later on. And I'm going to pass it on to Jonathan for the nose cone.
All right, nose cone. Some overviews. We just want to withstand the aerodynamic forces of just under Mach 1. And has to couple and disengage from the nose cone coupler for recovery. Has to fit the parachute and drug within it, and withstand shock forces from main chute deployment. And then the big one is withstand temperatures and continue to have structural rigidity while it's sitting under the sun on the pad. And then survive hitting the ground under the main parachute. So quick overdesign view, there's a 7-inch section to meet one of the DTEG requirements, forget the specific one, but the curve section is 26.25 inches in a ball and carbon curve. And the tip is a metal tip with an eye bolt of 5/16 inch in diameter. Manufacturing, it is 3D printed out of polycarbonate to meet the temperature requirements and aerodynamic forces. It did withstand the flight going up on their test flight. However, on the flight down, it did not like hitting the ground very much.
Okay, can I see the nose cone in the camera?
All right. Can you repeat that?
Yeah, can I see the nose cone in the camera?
Yeah. All right. There you go. I think so. This is our current nose cone. It's not currently epoxy together. That's planned to be tomorrow. Okay. But you can see there's mating lips on each one that'll get epoxy together, and those are able to withstand holding the rocket together. And then both shear bolts. Yeah, this is the easiest one to get off because it's pretty toleranced.
Okay. What do you use to join the nose cone parts? Epoxy.
It's an epoxy. What was it?
It's Loctite EA 93.
Loctite EA 9340. Sorry, I forgot that off the top of my head. It's pretty strong.
Chosen for
Yeah, it was chosen for high temp rigidity. And it's used for other integration parts. Yeah, and then our tip is on the CNC lathe. Just a tip and a plug that can hold on to the tip on the top. It's not tested whether or not it could really, in a full test, if you can withstand the shock forces, but by pulling on it with about the same force that it should be able to survive.
Okay.
Yep.
Sounds good. Thank you. Okay.
Yep. Yep.
All right, so moving on to integration, just as a project overview, our main purpose was to combine all of our individual parts of the rocket, which includes the 3 airframes and the nose cone. So we kind of go over that going forward. So our 4 main parts that we have are going to be the nose cone coupler. That is what's going to connect our nose cone and the upper body tube. And then below that, for our airframe section, we have 2 different composite sleeves, one to connect the upper body tube to the fin can, and then the second one connects both of the fin cans together. And at the very bottom of the rocket, we have an aft ring enclosure. This is where we're going to be holding the motor in place and securing it in the rocket, as well as transferring the thrust to the rest of the rocket from that point. And some changes that we made from our test launch is initially we manufactured our nose cone coupler with tubes that didn't extend one full caliber into the nose cone and upper body tube. It was only 5 inches before, so now we're changing it to be 6.75 to stay with the DTEC 8.5 rule of having one caliber. We also removed our initial thrust plate and replaced it with a more traditional design, which is why we're having the thrust be transferred through the aft ring instead of our old design, which was through like the top of the fin can.
Okay.
And then I'll pass on to Matthew.
All right, hi Walter.
Right.
So I don't know, can you actually hold this real quick? This is our nose cone coupler from test launch. Can you see that on the table?
Yeah, I can see it. Thank you.
Okay, yeah. So like Anthony said, if you notice, our tubes were only 5 inches prior. The changes that we're making now is it's going to extend one caliper in to each upper body tube and nose cone.
Okay.
The initial requirements for our nose cone coupler, like said before, connect the nose cone and upper body tube to house the payload and recovery electronics, as well as withstand the shock force from parachute after nose cone ejection. And then we also aimed for having a simple design for ease of manufacturing. Can you go to the next slide?
Okay.
On the slide now is our bulkhead. So some initial design goals were to mill out pockets to reduce weight, as well as maintaining integration with our recovery. As you can see, there's 2 similar hole sets in 2 of the pockets. Those are for our CO2 canisters, as well as 1 set of holes for our recovery electronics to pass through. And then finally, we have a 3/4 inch diameter eye bolt that goes to the center that attaches to our parachutes and withstands the shock force of our nose cone ejection.
Okay.
The most complicated design was the recovery cage. So this houses our payload insert. The reason why we have those large pockets is for our payload to be accessible to the outside of the rocket for connection for our GPS tracker. This entire recovery cage is the longest part, and it's on the outside of the rocket, as you can see in the bottom picture. It's about 7.25 inches in length, and we have 6 bolt holes that attach to the payload insert.
Okay. That nose cone coupler deploy with the nose cone or is separate in the
So
section?
if you go back to the previous slide, you can see the eye bolt that's connected, that will be connected to the parachute. So
Okay.
the coupler itself stays with the upper body tube, and then the nose cone and the chutes eject off of it.
Okay. Perfect. Thank you.
For assembling the nose cone and manufacturing it, we decided to epoxy instead of weld. This was because we found that epoxying would be easier, as well as more simple and consistent, rather than welding, with less risk factors of messing up. The CAD designs are just to show the female and male lips between the bulkhead and the tubes. If you go to the next slide, Bianca, this is the entire nose cone coupler separated into each part. So there's the upper tube that goes into the nose cone, and then the bottom tube that goes into the airframe, and the cage, and the bulkhead. And once epoxied all together, it forms the nice nose cone coupler on the right.
Okay.
And then just some of our manufacturing resources. You can see us manufacturing the pockets on the bottom left for our test launch, but we've mainly used the lathe and the 3-axis and 5-axis mills, as well as the 3D printer for caps. But yeah.
Looks good.
All right, thank you.
All right, and then moving on to our composite sleeves. So like I mentioned earlier, there are 2 different ones. You can see, oh, can you refresh the slide? Sorry. Yeah, thank you. So we have one that's going to connect the upper body tube to the fin can, and then the one on the bottom connects the 2 fin cans together. They are identical in design and manufacturing process. And the main reason we did this was to kind of keep it lightweight. And a big thing was brought up to us by our mentor was talking about bending moments. So having them being that long and still have the same rigidity as the airframes made it very safe to use. And by the DTEG rule 8.5, all of our coupling joints had to extend 6.75 as well. So that is in complete compliance with that rule as well. And each of them is going to weigh about 1.44 pounds.
Okay.
And for manufacturing, we basically lay up the exact same way as airframes does, which will be explained later by our airframes lead. But after laying up our airframe, we will cut out a section along its length, and that way we can kind of squeeze it in to reduce its circumference, and then slide it into the airframe, and then epoxy them in together. And then the next part we have here is the aftering and the closure. Like I mentioned earlier, this is going to be securing the motor inside of the rocket and also be transferring our thrust. So there's going to be two separate parts for this. We have the actual closure, which is going to be the one that's going to be epoxied into our fin can, and it's going to transfer all that thrust into the airframes and into the rest of the rocket. And the little like ring with the branches on it, that is just going to hold the motor secured in place so it doesn't fall out the backside. And then for these parts, we mainly use the lathe and the water jet for the closure.
Just again, my name is Jonah. I'll be presenting on the airframes. So for requirements for the airframes of our rocket, we need it to integrate very seamlessly with all the other components. It needs to survive the loads as they are load-bearing airframes, and also providing aerodynamic structure for the rest of the rocket. For our basic design, we have 3 body tubes that are epoxied together with the composite sleeves mentioned before. They're made out of Hexcel M70 epoxy system with ACGP 193 weave. And we have 6 plies at orientations of 0 degrees, 45, 0, 0, 45, 0. So for manufacturing, we made these airframes on a mandrel. We rolled the mandrel, and every 3 plies, we debulked with a vacuum bag. And then after we put all 6 plies on the mandrel, we vacuum bagged it once more time and then put it in an autoclave to cure. As you can see on the top right, that's our cure cycle, and the bottom is rolling. Now to do a verification on the airframes, our primary failure condition we were concerned about was bolt hole tear out from the deployment of the parachute. So we conducted 2 different types of tests, both using the ASTM D3039 testing standard. The first was just a straight tensile test, so pulling on a 10-inch coupon and finding the failure. And then the second one was a sandwich bolt hole test to kind of study how the loads would affect the bolt holes on our rocket. And then we laid up and the coupons in a very similar way as the rolling and the manufacturing, so that way we could have accurate tests. So here are the results of our tests. The shock force from the parachute is 556 pounds of force. Split amongst the 6 holes, we have a single load of 92.67 pounds force. In the top right, you can see the pure tensile tests, and in the bottom, you can see the bolt hole tests. And given the loads that they were able to survive, we were able to calculate the factor of safety. And our chosen ply count was 6 plies. While all 3 parameters would have had a sufficiently high factor of safety, we decided on 6 plies to still have that rigidity and to allow easier integration with a lot of the other components.
All right, so moving on to recovery. Our rocket uses a 2-stage parachute deployment system, primarily with a drogue descent phase at apogee and then a main descent phase at 1,000 feet. These are the rigging diagrams for each of those modes. On this first image, you can see that the nose cone here still remains attached to that eye bolt. It's just separate from all the rest of the rigging, and all the rest of the rigging and the parachutes as well. Those will be stored in the nose cone. Then once the rocket descends to 1,000 feet above ground level, the main chute deploys. And that deployment is initiated by a parachute stage separator. It's a tender rocketry tender descender that's commercially available and off the shelf. Yeah. So moving on to the electrical components and the like actuation methods, we have our 2 Blue Raven featherweight altimeters. Those are also commercially available. And those, we have 2 of those on board in our electronics bay. Each of those is wired into the electronic matches, which detonate our black powder charges, which are in our CO2 pressurization system, which I'll get to later. Here you can see what those wiring diagrams look like. Each of those altimeters is activated by a arming switch. There's 2 of those, one for each separate altimeter. And we also have the featherweight GPS tracker that's good for 300,000 feet of range, and it has about 16 hours of battery life. That is also stored within the recovery avionics bay as well. This is what that avionics bay looks like on the left. You can see those 2 rectangular looking things are our altimeters. You can see the antenna of the GPS there as well, and the arming switches are above. And on the right, we have a top-down view of the upper half of the nose cone bulkhead. There's an amphenol connector there that takes all the wiring from the altimeters and passes it to a screw terminal block, which we use for better wiring management for the tender descender and the CO2 pressurization systems. And we have the eyeball as well, which is where all of our rigging will be attached to. Moving on to the CO2 pressurization system, this is a student researched and developed design. It is a black powder initiated system. So we have a spike contained within a piston here. In the charge cup, there's about 1 gram of black powder and 2 E-matches. One of those goes to each altimeter for redundancy. At apogee, one of those activates and punctures the primary CO2 canister, and that pressurizes the nose cone and ejects it. And we have a backup charge that is roughly twice the amount of that CO2 that deploys 2 seconds after apogee in case of a failure to pressurize or a failure of the primary pressurization system. Moving on to shock force calculations, we were estimating a 450 pounds force of opening shock on the rocket during the deployment of the main chute. These calculations were performed based on a software called OSCalc, which is a tool developed by Parks College. We input altitude based off of above ground level ranges, so that's accurate to the flight conditions at New Mexico, and we use the estimated descent rate under the drogue for the rate of airspeed as well for that. And this gives us a range based off of factors like parachute inflation time and rigging elasticity. And all of the loading under the main chute is transferred directly to that eyeball as well. With that, I'm going to hand it over to Ashlyn for payload.
Excellent. Thank you, Alex. My name's Ashlyn. Our payload lead unfortunately could not be here, so I will be presenting on his behalf. So the main requirements of payload has a weight requirement of 8.8 pounds or greater. We are aiming to record video footage of the vehicle during launch and recovery. I'll get into it later, but it'll be a live video footage stream. We also require that the payload be independent of the rocket and fully removable for inspection at the at Spaceport. One of the secondary goals is to transmit 1080p 60 FPS video to the ground station, along with telemetry data that will allow us to have a live flight profile of the rocket during flight. So we are using a walk-snail avatar video camera and transmitter, and it meets the 1080p 60 FPS requirement for the live video challenge that we are hoping to participate in. This is directly transmitted back to the ground. The range is 13,000 feet. This is something that we are testing at the moment. Our local recording will be made and viewable post-launch with up to 32 gigabytes of storage. The telemetry is gathered separately using an Arduino, and it will be overlaid live, so we can view all of the coordinates and altitude and velocity. So our sensor package will log all the relevant data to a micro SD card. And again, this will also be transmitted back to our ground station. All of these sensors are integrated together on a PCB, including a GPS, an inertial measurement unit, and a barometer. Our flight computer is secured to the same PCB as the sensors, and an antenna mounted to the payload insert. The Arduino has native LoRa transmitter, which only requires one additional antenna and no separate transmitter module. Okay. So the telemetry module and video transmitter each have their own frequencies. This is important for Spaceport as they assign each team frequencies so as not to interfere with each other. So these each have a large range of frequencies that we can tune to meet this requirement. Okay, so onto the payload insert. It's something that we've shown you already. You can take that off. Awesome. So this is our payload insert. It does house recovery electronics as well, but those do not count towards our mass requirement. We're only counting the actual payload mass for that. So this core is 3D printed using polycarbonate with 3 main chambers. We have our video in this, and then our other sensors in this chamber here. We have metal inserts in these empty slots to provide integration points to the payload coupler, so we can avoid screwing into plastic and requiring that to be structural. So it's easily removed before assembling the rocket. And I think we can move on to the next slide. And I mentioned the integration points, but yeah.
Okay.
Awesome. So for testing on our launch and Brothers organ, we lost reception to the video transmitter a few seconds after launch. In order to remedy this, we have moved antennas to be 180 degrees apart from each other, hopefully to maintain a better connection with the ground. We are also doing testing later this month to make sure that we can transmit at the ranges that we need to. But awesome.
How's it going? I'm Finn's lead. My name's Beckett.
Right.
Yeah, so main requirements of the fins, we need to provide the rocket with proper stability margins, so 1.5 to 4 calibers as per the DTAG rules. They need to be comprised of lightweight materials. We utilize carbon fiber and carbon fiber like filming adhesives. And then also the fins must withstand aeroelastic forces throughout flights, so things like flutter. And the main function of fins is to allow us to achieve 10,000 feet, at least 10,000 feet of altitude, a straight flight profile, and minimal spin. And kind of our team goals that we're experimenting with this year is the use of pi preforms or pi bonds, as you'll hear them referred to as. They are 3-dimensionally woven carbon fiber joints that join our fins to our fin can. So the fin can construction is made of three main parts. It's made of the main fin, which is 18 plies of carbon fiber prepreg. The fin can, which Jonah went over, it's a 6-ply carbon fiber fin can of the same material as the main fin. And then we also assemble the fins to the fin can using pi bonds, pi preforms. And then after we're done assembling those 4 fins onto the fin can, we do 2 overwrap plies for each fin on each side of each fin, which increases our overall average thickness of the fin, which is super important for maintaining so we don't flutter, or like the fins don't fracture under flutter. And then the materials are just listed below.
Okay.
Here are the main dimensions of our fins. So we have 4 fins. The root chord's 12 inches. The span is 6.5 inches. We kind of arrived to these dimensions through open rocket simulations, and we were able to test this this fin geometry at our test launch. And the rocket had a straight flight profile, and there was minimal spin, so it did exactly what we wanted. And then kind of a note, our max stability is 3.57 calibers, which is well within the rules per DTAG, the DTAG rules. So yeah. And here is the overall construction. This is just a CAD screenshot. As you can see on the right, we have our main fin in the center there, and it actually intersects through the fin can with 2 fin tabs. And this just allows us to index the fins properly into the fin can. And then you can see the pi bond, which is kind of shaped like an upside down pi symbol. That's where they get their name. And it allows the fin to bond to the fin can. But it's important to note that this relies on filming adhesive to make these bonds actually strong. So it's a structural filming adhesive that's primarily used for bonding metals to composites, but through testing, we have seen that it works for bonding composites to composites.
Okay. Can I see the fins in your rocket?
Yeah. So I'll hold up the fin can here. So you can see the blue material is the filming adhesive, and then about an inch up from the base of the fin is where the pi bond kind of exists. And it's got about a 3-inch base width that goes the entire length, the entire root chord of the fin. So
Okay.
yeah, okay. Yeah. And then I didn't really need so kind of going over the failure modes for the fins. We have fin flutter and then landing loads. Going over fin flutter, we looked at NACA technical note from the 50s, which a lot of people use for validating their fin flutter. And we calculated using a MATLAB script 83.84% margin of safety. So fin flutter will not occur during flight unless we go really fast for no reason, which we won't. And then landing loads. So landing loads were difficult to calculate before test launch, but now that we have test launch data, and we saw that the fins did shear off due to malfunction with our main chute opening. With 2 fins breaking off, we were able to see that there wasn't a substantial bond between the pi bond and the fin can, and this was due to improper bond prep, which we realized and then proceeded to test after this launch. So go to next slide. Yeah, so we were able to do some Instron testing, some lap shear tests to prove that bond prep does actually work. And the bond prep that I'm talking about is after we cure the airframes, there is a residue on the outside of the airframes just from curing them. And so we made sure to sand the bond surfaces all the way to carbon fiber, to raw carbon fiber, and then proceed with the bond. We did not do this for our test launch, and so that is why 2 of our 4 fins fractured off. But we have very high confidence that this won't happen under ideal landing conditions. Yeah. And here are some more of those results. We saw a 159% increase in the maximum load that a properly bond prepped coupon could take. So this gives us just a lot of confidence. The manufacturing process for our fin can assembly. Our main fin is, like I said, it's an 18-ply solid laminate carbon fiber, and they are water jet to their final shape. The fin can airframe, or the lower fin can, is manufactured exactly the same way that Jonah explained earlier in his slides. And then in bonding the fins to the fin can, like I said, we go through proper bond prep. We sand all the surfaces that are being bonded to raw carbon fiber. We temporarily cure the fins to the fin can before we oven cure everything. And this ensures that they're properly indexed into the fin can. Then we lay up bags over that and oven cure it. And it's the same oven cure that our pie bonds take. So, and then afterwards, after we're done curing everything, we by hand post-process the.
I think that's also it for our presentation. Do you have any follow-up questions about any of our systems?
You're still muted right now.
Sorry, yeah. Yes, I have a couple questions. Actually, Ezra gave me a checklist just to confirm the information. Let me share the screen.
Oh yeah, no problem.
You can see it?
Yeah. Yes.
Okay. It's pretty simple, but just to confirm the information. With the Nosecone, I don't have any question. With the recovery, the shot cord, you can tell me the material, the leg is okay, the thickness and material, just to confirm the material that you use is Kevlar, nylon.
The
The
parachutes are made of ripstop nylon.
Okay. The shot cords, what is the material?
Those are also nylon, and they are, some of them are Dyneema.
Okay, it's a tubular nylon? Or
I'm sorry?
It's a tubular nylon?
Yeah, the shroud lines to the chutes are nylon. And there are Dyneema ropes as well that are included there.
Perfect. I don't. You use sharpins in your rocket?
Yes,
How many use them, and what
we
is the
use
size?
we use 3 1032 nylon shear screws that hold on the nose cone during flight. And then those shear off when the nose cone is pressurized by the CO2 canisters.
Okay. Okay, I don't have any question with that. I don't have the quick links and hard points. Quick links. You mentioned the material.
The quick links are, I didn't mention it, but they are made of stainless steel, and they're rated up to 3,500 pounds of force.
Okay, perfect. Bend holes. Do you use bend holes in your body top, in avionics, or
Do you use what? Sorry.
bend holes?
Vent
hole.
Vent holes. Oh.
Yeah.
We have. I'll see if I can. Oh, where are they? Okay. So
You are.
there are. I don't know how easy this is gonna be able to. You know what? I have an extra one, I think, or I can just.
You can use them.
I'll just use this one. So, to someone in these these two cylinders here are the CO2 canisters, and those have vent holes on them. I can go back to the presentation as well. Unless you're, oh, are you talking about vent holes for the barometers and the altimeters?
Yeah, for the altimeter, sorry.
Okay, yeah,
you-
there will be vent holes drilled into the upper airframe for those to equalize.
Okay, they already made it. Is are in the body tube? Or you
Yeah,
need
they're
to make it? Okay, perfect. The rocket markings is the team number, the frequency already in your rocket, or you need to.
those will be the team number marking. Those will be on the brass.
Yeah.
On fins.
We haven't wrapped it.
Yeah, once we wrap it, we'll have the team number and everything on the fins.
Okay, perfect.
Mhm.
Don't forget to put the center of gravity and center of pressure in your rocket.
Okay, sounds good. Those have to be visible on the wrap as well.
Yeah, okay,
Okay.
perfect. You already have the motor?
Yeah, we're doing CODs.
Okay.
Mhm.
It's okay. With payload, I don't have any couplers, material, structure, thickness, shoulder leg. Okay. What more? Actually, I don't have too many things in your rocket. It's a very good project. Okay. Okay. Well, for me, it's okay. I don't have any more question about your rocket. It's pretty good. I see all the information uh, on your submitted progress. And just for information, this year is your first year in the Spaceport.
Say again?
It's your first time in Spaceport.
This team, yes, we competed in 2019, but that was a completely different team. Like same team, different people.
Okay, perfect.
Mhm.
About your checklist, you already have the checklist of your rocket?
Yes, it should be on the the technical report if
Yeah.
you receive that. Yes, it should be on there.
I don't receive yet the technical, but I see it.
Okay.
Okay. This year, Evra provide all the teams tables and tents. You only need to come with chairs just to keep it. Don't forget food, water in the launch days. I send you by email all the recommendation for me for all the teams to the close and another helpful information. I don't know if you have any question about the competition. Oh, well, I'm sorry. For your rail bottoms, you just to confirm, you use 15 rail bottoms.
Yeah, I believe so.
Okay, perfect. More materials. Okay. Well, I send this document by email in in a few minutes just to keep it. Do you have any question for me for the competition about the flight safety review?
Any questions? I think we should be all good. Oh, Ashton might have what, maybe?
I think we're good, but thank you. We really appreciate it.
Okay. Okay, perfect. Well, for the review is all. If you have any other question before the competition, just contact me by email.
For sure.
And I send you all the feedback about the review today in a few hours with this document. in missile. Thank you,
All right.
guys.
Sounds good.
All right.
Thank you so much.
Thank you.
Thank you.
Okay, bye, guys. Have a good day.
Yeah, you
you.
too.